Okay, so last time we met and introduced the concept of Boyle's law, because what we did is we took a gas and we took some measurements of the pressure in pascals and the volume of the gas in centimeters cubed, 1 over volume. So we had some data. I'm not really going to write a load of data out. And what we did is we plotted some graphs, and we saw that if you plot the pressure against the volume, you get a graph that looks something like that. Whereas if you plot the pressure against 1 over the volume, you get the pot of gold at the end of a physics rainbow. So I'm going to use the rainbow one. You get a straight line. Okay, and what that led us to was the essentially statement of Boyle's law, which is that for a fixed mass of gas at a constant temperature, the pressure times the volume of the gas is constant. And that is the sort of the statement of what we call Boyle's law. Now, what we're going to do is today we're going to see how we can kind of use that to actually work things out, because as a sentence it's kind of there, it's what the law is, and we've got our sort of assumptions. We're assuming that when we want to do this we have a constant temperature. I'm going to assume that the mass of gas is always going to be the same, because otherwise, say, our balloon would have a leak in it. But we're going to think about how we can maybe use this to solve problems, because what we saw is that so we saw that, like, you know, for our gas, pressure times volume is equal to a constant. Okay, that's it sort of written out mathematically. Now, why is this useful? It was useful because it means that, given that this will always be the same, I think last time we always got for the stuff we were using 42, 43 was our constant. And that constant is dependent on the gas that you're using and the temperature that it's at. So the constant isn't like a special number. It's not like the same number for every gas, but it's just for the gas you've decided to sort of mess around with. So what this means is that we can actually use this to make some predictions. Okay, so let's imagine, so we can deal with this and we can think about what this might do. Let's do an example. I should probably not have the most silly pen. So let's think about how we might be able to use this to work something out. So let's say we've got the gas with a volume of, let's say, 12.7 centimeters cubed, is at a pressure of, let's say, 150,000 pascals. And let's change the pressure. The pressure is reduced to, let's say, 115,000 pascals. What volume does the gas occupy? And so this is kind of how this sort of then a question sort of might be set up. So we have what was initially going on, we have our initial volume, we've got our initial pressure, we know a final pressure. Are we able to work out what the final volume is? And it turns out that we should be able to, because we can remember, and I'm going to just sort of color code these slightly differently. So I'm going to use this, that's going to be our final pressure, and we're after our final volume, and let's sort of highlight this as being our initial pressure, and this is our initial volume. Okay, so we know that from Boyle's law, pressure times volume is equal to a constant. That's what we know. So we can take our initial volume and our initial pressure, and we go, oh, okay, so that means that 150,000, our initial pressure, times by 12.7, our initial volume, is going to equal a number. So we could say this as 12.7 times 150,000, and we get 1,905,000. Okay, Pascal seems to be a cubed, I guess the unit would be, but I'm not terribly. It's not that important. So that's just the number. Okay, but we also know that that number has got to equal. We actually know, because this has got to be the same thing. We have our final pressure, so 115,000 times by our final volume, has also got to equal the same number, because that's what Boyle's law tells us. And so what this means is that, oh look, this is nice, because we can just say, oh okay, this times this must equal this. Well, that leads us to the idea of, therefore, that the final volume must equal 1905,000 divided by 115,000. What we get is 16.6. Well, my calculator spat out a horrible number, but I'm going to go with 16.6 centimeters cubed. And this is essentially how we can use Boyle's law to mathematically work out something that we don't know. So we had a thing we didn't know, and we're able to find out. And so as long as we don't mess around with the temperature and we don't let any gas into or out of our system, then what it allows us to do is to make these sort of predictions. We can say, oh, okay, what volume is this going to be? And this is helpful whenever we've got something that has been put under pressure. So if you come across, say, there's a deodorant is a pressurized container, gas cylinders like a helium balloon cylinder is a pressurized container. What that means is that you can, if you put a gas under pressure, when you let it come back to air pressure, it'll inflate, it'll expand, it'll get to take up a bigger volume, and that enables you to fill lots of balloons, even if you've got only one tank, depending on how pressurized it has been. So let's do another little example, and let's deal with a diver. So here's going to be, I'm going to draw a picture. So we know, you might hopefully remember, there's the sort of the land, and there's the ocean, because I've only really worried about two colours. And let's think we have a little diver down here. Oxygen tank. Okay, and so they're diving around, and we know a few things. So we know that up here, where the air is clear, the air pressure is equal to 100,000 pascals. That's what we know. That's what we've got out in the sunshine. That's normal standard air pressure. And down here we've got a person, and let's say they are, let's give them a depth. Let's say they are let's say they've dived to a height of, let's say, 54 meters. They're 54 meters down. Okay, and what they do is they blow out. They just sort of release a bit of air. So they release a bubble of air. Let's say that that bubble has a volume of, let's just say, 4 centimeters cubed. So a little tiny bubble of air, 4 cubic centimeters, and that bubble is going to rise up and rise up. And you probably get an idea of is, as this thing goes up, the pressure is going to decrease, and the volume of our bubble, as the pressure goes down, it's just going to get bigger and bigger and bigger. And eventually, what we're interested in, just as it hits the surface, as the pressure becomes 100,000 pascals, what's the volume? What's the volume here? Okay, so let's formalize that as a kind of a diver is 54 meters deep. They release a bubble of air with a volume of 4 centimeters cubed, or 4 centimeters cubed. How big is the bubble when it reaches the surface? Well, this is a bit of a sort of a, just give this one example too. So first thing we have to do is we have to work out what the pressure is down here. Okay, we don't intrinsically immediately, it's not, the question's not told us, but it's given us the information to do so, or at least about to. I need to give you two bits of information, that G is equal to 10 newtons per kilogram, and the density of water is equal to 1,000 kilograms per meter cubed. I'm going to give you those two bits of information, because what this is going to first ask is we have to work out what the pressure at this depth is. And to do that, we have to use the equation that pressure, or the increase in pressure due to a liquid, is density times gravity times height. So, nasty, isn't it? So step one, so we've got to calculate the initial pressure. So the change in pressure due to, so the change in pressure is density times gravity times height. So from a liquid, density times gravity times height, and the information that we've got here is that we've got, therefore, density is 1,000 times gravity, which is 10, times height, which is 54. So we've got 54 times 10 times 1,000, and we've got 540,000 pascals. Now, that's not immediately the answer, because that's 540,000 pascals, and that's that water that's already sitting under this. So our initial pressure, we've got to remember that we already had air pressure pushing down on the water, And then we've got the water pressure pushing down on this person. So this person is essentially dealing with all that water and all that air. So they're dealing with a total of 640,000 pascals. So the total pressure on the diver is 100,000 from the air plus 540,000 is from the water. So that's 640,000 pascals. Now, in case you're worried about, oh my goodness, an exam question wouldn't ask me to do all that in one go. No, what they would do is they would first have a question which says calculate the pressure due to, say, 54 meters of water, and then they would have a second question which is, you know, using your answer, calculate the total pressure on the person. So they'd give you that hint that you need to add those two things together, or it might be show that it's 640,000 and you get that and you realize, oh yeah, I've got to add the extra thing. So it sort of led through. Anyway, now we're in a position where we can start to use Boyle's law. So because we've now got our, let's say, do that, we've got our initial pressure and we've got our initial volume, and I'm using the wrong color. I've just messed up my color scheme there entirely, so I'm going to undo that. That's upsetting. So we've got our initial pressure, which is that. Got our initial volume, which is that. And we know our final pressure, which is what I've done there. And I do appreciate I have reversed my color scheme from the previous example. You'll just have to forgive me, or just send me an angry email. I'm sure I'll read it. Right, so let's deal with that. So we've got pressure times volume. So, or initial. So that's going to equal, initial pressure is 640,000 times by the volume, which is 4. Simple. Times 4. And we've got 2.56 million. Okay. Okay. Now that's obviously going to equal our final pressure. Times final is equal to 100,000 times V, and that's also got to equal 2,560. So fantastic. Oh, that's a nice easy one, because it's just that divided by that. So V is equal to 2,560,000 over 100. And we get 25.6. So that small bubble, divided by 4, that small bubble has increased of about 6.5 times in its volume. And that's why if you have any form of a leak of any pressure, any gas at the bottom of something underwater, what you end up with is quite turbulent bubbles getting up to the surface and hitting the surface, because by the time these small bubbles get to the top, they expand by quite a large amount. And essentially, that's what we can do with Boyle's law. And it doesn't matter, ultimately, whether they're dealing with initial pressure, initial volume, final pressure, final volume. You'll know 3 of them. And so it just becomes a question of working out, finding the one that you don't know. So in many ways, the tactic for this is very similar to solving balanced moments problems. It's very similar to solving the momentum problems. You know what the initial case is. That has to be the same as the final case. So you've got a balance of something that has to essentially be the same on both sides. Now, this occasionally, in order to sort of make it a bit smoother without constantly having to write out this sort of value, whichever it is, because it's different for every different case. Boyle wrote this as a slightly shortened thing. So Boyle's law is often rather than it being, rather than doing all this, you can write it as, so let's do, I'm going to use my blue and my green. So P1 times V1, so in first pressure, first volume, equals P2 times V2. And this is often how it gets sort of written. I don't know if this points to that. Oh, it's because it's too thin. That's why. Yeah. And this is often how it actually gets written sort of mathematically, because we're not really interested in what this constant in the middle is, because as I said, it's different for every different case. It doesn't represent anything special. So it often tends to get written as this. So, this is so where P1 is the initial pressure and V1 is the initial volume. And P2 is equal to the final pressure and V2 is the final volume. So using those together, it's possible to, you can sort of write what this would be. This sort of, you rearrange it. If you want to know the pressure, then it's P1 times V1 divided by V2. If you want to know the final pressure, it's, let's keep the color scheme probably, so P1 times V1 over V2. And if you want to know the final volume, well, it's P1 times V1 over P2. And you can sort of see that is just the value of the constant, because we've worked it out anyway. We just don't need to necessarily write it down. And there we go. That's mathematically how we can use Boyle's law with a couple of sort of examples. And so what we're going to do is a bit of practice using it. So awesome times.